Yep, I think we're good to go. So basically, all right, morning everyone. Welcome to, I guess, session 1C. I'll be the chair, so if you have questions, I'll be monitoring the chat. Keep yourself muted. And for the speakers, I'll do basically this 2 minutes before your time is out, just so you have like a kind of silent reminder. Other than that, let's get going. So the first paper is Low Degree Hardness of Random Optimization Problems by Alkosh, David, and Alex, and Alkosh is going to give the talk.
Hey, so thanks. So what I'd like to talk about today is some recent work with Alex and David. You can think about it as sort of from two different perspectives. You can think about it as sort of results about average case hardness. I like to think about it as questions about randomized optimization problems. The kinds of examples you need to keep in your mind are things like, say, maximum independent set problem on a random graph, optimizing random polynomials of fixed degree, looking at things like, max k-sat with random clauses. So there's, a big literature about these kinds of questions. And so typically, things people are interested in are, for example, there's things like, for a typical realization of these problems, what's the best sort of objective value? What's the optimal value? And then sort of on the related side from computation, what's the typically for a typical realization of the problem, what's the best value you can actually achieve efficiently? And then, when these two values, the best possible value and what you can efficiently achieve aren't equal, then, there's the question of, is there some sort of structural or fundamental reason for this? So there's been a lot of, really nice work in recent years on structural evidence for, this gap in average case. There's works related to what's called the overlap gap property, which I'll talk a bit about today. There's things called shattering. And so in this direction, you'll prove some sort of structural property of the landscape of the corresponding function. And then there's the matter of going from that structural property to an actual refutation for some class of algorithms. So a lot of these refutations have focused on specific families like MCMC methods, approximate message passing. But there are also some sort of larger families like local algorithms in the sparse setting. But unfortunately, when you work in these sort of algorithm by, sort of these more specific families, some of these results end up not being optimal in the sense that the family of algorithms we end up knowing actually aren't going to do as well as the best possible family. So an example would be like MCMC with the random start. Will not perform as well as something like tensor unfolding for a problem such as tensor PCA. And so then the question is, can we come up with sort of a fairly broad class of algorithms that will work in many different random optimization problems to prove sort of lower bounds against? So, one candidate would be like local algorithms, but this is sort of confined to the sparse setting. More recently, there's been a lot of attention to sum of squares types of methods, but recent work has shown that the sum of squares, in fact, doesn't do as well in some of these random optimization problems because it's trying to solve a slightly harder question than just optimization. And so what I'd like to talk about today is sort of the low degree method, which has been emerging from the related statistics literature. And so the idea here is we want to provide lower bounds against low degree polynomials, by which I mean the following. It'll be, the algorithm will be something that can be described as, I take in my input, say if it's a graph optimization problem, say the adjacency matrix of the graph, and then the output will be some vector, which is supposed to be our near optimal solution. And that vector needs to be such that its entries are all polynomials of bounded degree in the input matrix, or the coefficients of the input matrix, rather. So some examples of low degree methods are things like power iteration, approximate message passing. In the dense setting, in the sparse setting, local algorithms also fit into this framework, but also things like, doing any of the above plus a pre-processing step. So for example, if you think about, with tensor cases, if you start doing an unfolding thing and then do something spectral, this would fall into this class. And why low degree? Sort of the idea is that low degree polynomials or polynomials of degree d should correspond to sort of n to the theta tilde of d time algorithms. So as I mentioned, our motivation for considering this class is, it's, has emerged from the corresponding statistics literature where you're considering, questions like testing, but also related questions of estimation, where you're interested in finding what would say are called planted versions of these problems, where it's not I'm just trying to optimize a function, I'm looking for a specific optimum. So things like planted clique, etc. And so, what's nice is that in the sort of estimation and testing setting, what we find is that, the best algorithms are low degree. And furthermore, the low degree methods can be shown to fail in the sort of expected hard regimes. So some examples of results we can show is, one example is, so take maximum independent set on a sparse Erdős-Renyi random graph. So, the typical optimal value is, twice log d on d times the number of vertices. But the best sort of efficiently achievable algorithm we expect to in fact be half of that. And it can be achieved just by something simple like greedy. And, there's been structural evidence that this is in fact the threshold. And now we know for, by some important works in recent years that local algorithms, for example, can't beat this greedy threshold of half optimal. And so one consequence of our work is, low degree methods also won't be able to beat this, in the sense that if you take, any low degree polynomial in the adjacency matrix where the degree is at most poly log n, then you can't with high probability have an output vector that's both roundable in the sense that its values are nearly 0 and nearly 1, and such that the corresponding rounded vector is actually the indicator function for a large nearly independent set. And in fact, so for us, we get the threshold, as you can see, it's not quite the true algorithmic threshold. And Alex recently put out a paper where he gets down to actually showing that these methods rule out low degree polynomials for actually up to the algorithmic threshold. So that's the sort of sparse setting. Correspondingly, a more dense kind of problem you could consider, say, suppose I give you a random IID random Gaussian tensor and I want to compute its injective tensor norm. Alternatively, you can think about as optimizing a homogeneous polynomial of degree p. Let's say, think about it on the unit sphere. So the optimal values related to what are called spherical spin glasses. There's a formula predicted by Crisanti-Summers and proved recently. And in these settings, there's this conjecture coming from the physics literature that, there's a certain algorithmic threshold that's well below the optimal threshold. And recently, there's been some really important work by Subag showing that there is, in fact, an algorithm that achieves the algorithmic threshold, the conjectured one. And so as a consequence of our work, we show that, again, for any polynomial of sort of any p tensor where p is at least 3, no polynomial with an input of the tensor can put out a nearly optimal solution that's both nearly optimal and normalizable with overwhelming probability, and provided the degree is, again, say polylog n. And p is equal to 2, of course, in this case is just computing an eigenvalue. That's why we leave that out. So just sort of briefly, what are the main ideas? Sort of the key point is that, problems, many of these problems exhibit what's called the overlap gap property, and specifically 2 forms of it. The first form is saying for a random instance of these problems, any 2 near maxima are either fairly close or fairly far from each other in a quantitative sense. And then the other flavor of OGP says that if I take, say, my input graph, and then I resample a small fraction of the edges and look at my near optimal, independent sets for these 2 different graphs, these sets should be essentially, have essentially no overlap to each other. So that's one ingredient. And then the other ingredient is that you can show that these low degree polynomials are stable under, perturbations of this flavor, like under, on what we'll call, say, noise stability, resampling a small fraction of the edges. And then the key point is that there's this sort of meta theorem, which is that if you have, these two kinds of OGP, then, reasonably sort of noise stable algorithms should have a corresponding refutation theorem. And this has sort of been building up by a work by David and several co-authors. So I think that's it for my time. So thanks for listening.
Thanks, Alkosh. Are there any questions for Alkosh? You can either post them in the chat, or since this is the Q&A, you can also feel free to unmute yourself and just ask it if you prefer. Okay, if not, I have one, I guess, to get us going. So, Alkosh, so I guess, is this somehow, so like the very last slide that you had for the techniques, right? So I guess somehow morally this is kind of translating these kind of interpolation-based proofs that you have for just kind of like the usual local algorithms, and then trying to kind of like merge them with a kind of noise stability. Like, is that sort of what's going on, morally speaking, in the proofs?
Yeah, morally, that's kind of the idea. It's like, I mean, essentially, yeah, I would say that. It's like the idea is that, overlap gap property tells you have two near optima. That if you have, like we said, type 1 says if you have two near solutions, they're either near or far. And so then what you do is in the proof, you resample the matrix a little bit, and then you have two different runs of the algorithm on these two different things, and then you sort of connect them by an interpolation and show that you have to somehow violate one of these two OGPs if you were able to produce a good algorithm. So yeah, it's exactly the same sort of flavor of interpolation, except now you have to use noise stability rather than something a little bit stronger.
I suppose another kind of related question, which is like, does this, I guess, can you fit in this framework something like basically solving and rounding with some simple rounding, some simple SDP, like maybe some like low degree sum of squares relaxation?
I believe so. Yeah, Alex, do you have a comment on that? I mean, I think if you do something spectral, like sum of squares, that part will fit in. And then what we refute is, we don't refute sort of general rounding. Instead, what we say is we refute producing a vector which is sort of reasonably roundable. So for example, like, for the maximum independent set, we don't refute all possible rounding schemes for polynomials, but what we would do say is, we want an algorithm that produces a vector which is, most of the values are sort of on one side or the other of some natural threshold, and thus are reasonably roundable. Does that answer your question?
So regarding the SDP, I think, like, if you were actually running an SCP, it's not clear how to write that as a low degree polynomial. But often these methods coming from sum of squares, like, sum of squares give you some SCP. In many of the problems we know, it seems to be the case that you could take that SCP and turn it into a spectral method that does just as well. And that kind of spectral method can be written as low degree. But so that step's kind of conjectural, but sort of believed to hold in some kind of broad generality.
And then Sam had a question: are there examples where type 1 or type 2 fail and the theorem clearly fails?
So for example, like if you take just computing an eigenvector, I think type 1 should fail. And then of course, you can compute an eigenvector efficiently by power iteration.
Cool. Very nice. All right, so maybe we can have the next speaker set up. Let's see, who do we have?
Yo.
Hello, we have Morris. Excellent. Do you want to share your screen?
Yeah, let me try doing that.
All right.
Can you see my screen and not see my presenter notes?
We can, in fact, see the presenter notes and the entire presenter screen.
Oh, that is very unfortunate.
I do not think you can do like, I think you have to do either one or the other. Like either you have to be not in presenter mode or we'll see your presenter notes. I don't think share screen works any other way on Zoom, unfortunately.
Oh, really? Okay.
Yeah.
Well, that is unfortunate.
That's fine though.
Let me see. How could I get this to work? Okay, I guess what I'm going to do is I'm just going to play this and do it from memory then. Cool. Oh, well, I don't. And how do I play it without presenter notes?
What happens if you do Keynote Live?
What's Keynote Live?
That's
the one next to the play. Yeah, there's like a button next to play. Yeah.
Oh. Okay, so wait, how do I play without the presenter notes then?
Do you have a second screen actually?
I have a second screen.
Yeah, if you, I believe if you disconnect your second screen.
Oh, I see.
Yeah.
Okay, cool. Well, since I don't have presenter notes, I'm just gonna kind of wing this then. So hey, can you see my screen?
All right, give me just 1 second just to announce the paper, then you can go. Yeah. All right, so now we have list decodable mean estimation in nearly linear time. It's a paper by Yeshwant, Sedant, and Morris will give the talk.
All right, cool. So I don't have my presenter notes, so I'm just gonna kind of talk about this. So this is list decodable mean estimation in nearly linear time. And this is some joint work with Yeshwant and Sedant and myself at UC Berkeley. So let me, okay. So let's talk about mean estimation. So I have x1 to xn. These are data points in d dimensions drawn from a distribution big D. The mean of the distribution is mu, and the covariance of the distribution is upper bounded by the identity. Our goal is to output an estimator mu hat such that mu hat minus mu in Euclidean distance is less than, say, a constant. Now this is very easy because you can just take the mean of the distribution, all right, the empirical mean. So this is easy. Now, what happens if there are some corruptions? So for example, let the inliers be x1 to x alpha n in RD, still drawn from the distribution D. But now we have an outlier set, x alpha n plus 1 to xn, which can be anything introduced adversarially with knowledge of what x1 to x alpha n is. And clearly, you know, your data points are not labeled to you in this 1 to n order. You don't know what the outliers are, right? So the key point is you have to identify the inliers and you want to find their mean, right? So you want to find the mean mu, and you still want to, you still want to output an estimator mu hat that does, reasonably well. Now for alpha greater than a half, this is the problem of robust mean estimation. And at this point, this problem is pretty well studied. And it's, it has increasing relevance because we find that a lot of robust statistics problems reduce to some form of robust mean estimation. So here we consider, this natural extension of the problem where alpha is less than 1/2. So still you have the same exact setup. x1 to x alpha n are in d dimensions drawn from a distribution D. And your outliers are x alpha n plus 1 to xn, which are again anything. It's just that alpha is less than 1/2. So your inliers are, a minority of your data set. Your goal, if it were to output a mu hat, an estimator mu hat, that is close to mu in Euclidean distance, you're going to fail. And you're going to fail because, the adversary could have introduced another sort of like cluster of points with a mean that is far away, but, covariance that is also bounded by the identity. And now you can't, you can't find your true mean anymore. And this is very unfortunate. So what do you want to do, right? So here's the natural, modification of the problem. You want to output, instead of a single estimator, you want to output a list of estimators, mu hat 1, mu hat 2 to mu hat big O of 1 over alpha, such that for some element of this list, for some estimator like mu hat I in this list, we know that mu hat I minus mu in Euclidean distance is less than, say, O of square root 1 over alpha. So this is sort of analogous to list decoding and the theory of error correcting codes, where when most of your data is, kind of garbage, you could still hope to output a succinct list of estimators, one of which is close to the true mean, right? So I hope that made sense. I hope it does. Actually, just to verify, can everyone still see my screen and stuff? And
Yeah, you're good.
Oh, I'm good. All right, cool. So this problem was introduced by Charkar, Steinhardt, and Valiant. They provided a polynomial and NDK time algorithm for list decodable mean estimation. And their algorithm achieved nearly optimal recovery. That is to say, they find a list element I. They output a list of estimators, mu hat 1, mu hat 2, all the way to mu hat O of 1 over alpha, where one of them is O tilde of root k away from the true mean in Euclidean distance. So just to remind you, k is 1 over alpha, and optimal recovery is O of root k. And what they achieve is O tilde of root k, where I think it hides like some root log 1 over alpha factor. But at any rate, that is what they got. And it's a polynomial time algorithm, and it was, rather well regarded. And here's our result. Our result is list decodable mean estimation in nearly linear time. That is to say, we have an O tilde of ND poly k time algorithm for list decodable mean estimation. It is the first improvement to Charkar, Steinhardt, and Valiant in terms of runtime. And we also achieve optimal recovery guarantees, O of root k, without the logarithmic factor. And this is nearly linear time when k is a constant, which for many applications of robust statistics, we think of, the amount of clean data you have as being, a constant. And that's a pretty reasonable thing to believe. So yeah, anyway, that's our result. And if you remember any slide, please remember this one. Cool. So taking a step back, what's list decodable learning? List decodable learning is, because clearly the question I just asked you, you can see that I could have applied it to more than just mean estimation. I could have applied this sort of question to any statistics problem, basically, or any robust statistics problem, right? So list decodable learning is a generalization of classical robust statistics to the setting of overwhelming outliers. It is also a generalization of planted problems to the semi-random setting. For example, semi-random planted click or semi-random planted independent set. I'm not going to go into these. It also provides a simultaneous generalization of robustness and clustering. For example, your adversary could have introduced a mixture model or a robust mixture model. And here the flexibility in the modeling is that the adversary can actually introduce all sorts of statistical structures into your problem. And that's why list decoding tends to generalize and capture a lot of interesting problems. And finally, there's something called semi-verified learning, where given an overwhelmingly corrupted data set, the goal is to perform inference using a small amount of side information. So we'll not go into this, but it turns out this is also equivalent to list decodable learning. So for our problem of list decoding, list decodable mean estimation of bounded covariance distributions, you can see that there's some related work for settling the polynomial time learnability of list decodable regression, the polynomial time learnability of list decodable subspace recovery, and for list decodable mean estimation of structure distributions. So I encourage you to look at this stuff because very little is known. And for our problem, there was some concurrent work by Diakonikolas, Kane, and Kongsgaard, which obtained an algorithm running in n squared d k squared time, and a subsequent improvement to ndk plus poly k time with the same authors plus Lee and Tian. Cool. So I hope the general landscape of the literature is clear, and I can start talking about our paper and our algorithm and how it works. So I'm going to do this sort of pictorially in like a sort of kindergarten style. So first, I talk about what a candidate mean is. We say a vector nu in RD is a candidate mean if it is the mean of a subset of alpha endpoints with bounded covariance. So a candidate mean basically is as good as any guess for what the true mean actually was, right? So an inefficient algorithm is to enumerate all candidate means in RD that are greater than omega root k apart in Euclidean distance. So the idea is just enumerate over the whole space, find all the candidate means, and then just only keep the ones that are not too close together. And that should give you a succinct list of estimators, one of which is close to the true mean. So clearly the mean of the inliers mu is a candidate mean, and thus the inefficient algorithm outputs a list of candidate means, one of which is O of root k Euclidean distance from the true mean. So how do we make this efficient? Right, so this is the key problem. So here's our algorithmic idea. Find a candidate mean mu1 hat, and then, delete the cluster of points near mu1 hat, and then find, the candidate mean mu2 hat and delete its associated cluster of points, and so on and so forth until you remove all the points in the data set. Right. So this is clearly very naive, right? So, here's a Venn diagram for what you should do. Start with a guess nu, some guess, like, some iterate. Now you ask the question, is nu a good candidate? If yes, then output it, If not, then you should update nu to be better, right? Okay, so clearly this should always work, right? Now, let me just sort of illustrate this. What you want to do is you want to find a good direction where you can sort of improve your current iterate if you find that it is bad. So it turns out that for the robust mean estimation problem, the direction in which you should improve your current estimate nu is the robust top eigenvector of the second moment matrix of the data set with offset nu. So that turns out to be what you should do, and this was something done in Cheng diaconical Ge. Now, for the list decoding problem, clearly this is this is rather difficult because you don't actually know where you should go because your top eigenvector could be of their covariance matrix can be completely uninformative, right? So this is a problem, and our main innovation is to find a direction to move that guarantees improvement. So I notice I'm running out of time, so I'm just gonna skip to the end. Oh yeah, okay, well, I think that's it. Cool. Any questions?
Thanks, Morris. Yeah. All right, let's kick it off with Ainesh. What properties of Gaussians do you need in the analysis?
What property? I don't need any property of Gaussians. It's bounded covariance.
Okay, that was a quick answer. Other questions for Morris?
Is this algorithm implementable?
Is it implementable? I mean, how good are you at coding? Right, all right. So like, is it implementable? I mean, I think some version of it is probably implementable. It might not get the same runtime guarantees, right? Like, we need to use packing covering STPs. So I doubt you could, you can't actually like run those kinds of algorithms. But somehow like, there are a lot of STP solvers that you can use. Like this is, there are ways to do this. So otherwise it's just a bunch of projecting and, moving. So I don't think it's that difficult. Yeah.
Would you want to run it in practice? This may be like, the other version of that question.
Would you want to run it in practice? I mean, would you want to? I don't know. Volition is a strange question. Like, that's a philosophical question. I defer it to the philosophers. Like, yeah.
All right. Question: does your algorithm work without knowing alpha? David.
Yeah. You do not need to know alpha. Yeah.
All right. Kevin, what's the role of multiplicative weights in a word?
What's the role of multiplicative weights in a word? Yeah. Okay. Well, that's a very strange question. Yeah. So,
you can use more than a word. How about that? I think maybe that was too challenging of a question.
I saw you skipped past multiplicative weights on the slides, and that's like my all-time favorite algorithm, obviously. So.
Oh yeah. So yeah, basically, you can solve SDPs using matrix multiplicative weights. So you have packing and covering SDPs. So typically you want to pack into like a spectral norm ball, but we need to pack into a ball that's not the spectral norm. It's actually a norm that is the sum of the top, like say k eigenvalues. So it's like kind of like a Schatten norm. It's called a chi-fan norm. And you want to pack into a chi-fan norm ball instead of a spectral norm ball. So we need to develop packing and covering SDPs that pack into chi-fan norm balls. And to do this, you need like, modifications of this sort of multiplicative weights framework for solving, fast SDP solvers. So that's actually the main technical contribution of the paper, is actually doing this. And this takes a lot of effort.
Maybe if we can stick it in the last minute. David asks, can you have better approximation guarantee if you output more centers?
Can you have, if you output a lot of centers, sure. Yeah, yes, the answer is yes. But I don't know, like you gotta, like how many is many, so for example, for list decodable regression, if you output more centers, like you can actually get a faster algorithm. So there's a bunch of this sort of like funny thing for I'm not sure for list decodable mean estimation, but for the other problems you can, which is kind of cool, right? Is there any other questions?
Thanks, Maurice. Yeah, I guess the rest of them we can take them offline if there are more. So all right. Next paper, Outlier-Robust Clustering of Gaussians and Other Non-Spherical Mixtures, paper with many authors, and I guess Inesh is taking the talk. So go for it, Inesh.
All right, thanks, Andre. So today I'll be talking about outlier-robust clustering of Gaussians and other non-spherical mixtures. And this talk is a result of two papers, one by myself and Pravesh Kothari, and another one by Ilyas Diakonikolas, Sam Hopkins, Daniel Kane, and Sushruth Karmarkar. For this talk, I'll be mostly using the results that appear in our paper, but this other paper obtains roughly similar results. Okay, so let me start by describing the problem of clustering Gaussian mixtures. Consider script M to be a mixture of k equiweighted Gaussians, where each component of the Gaussian is parameterized by mean μi and covariance sigma I. We then draw n samples from this mixture using the following random process. We pick one of the Gaussians uniformly at random, and we sample a point from it. What we end up observing is this set of samples. And the goal is to then accurately cluster these samples when clustering is possible. So I'll describe what it means to be well separated and when clustering is possible and what an accurate clustering means. But before that, let me set up some notation. So the set of samples that we observe, x1 to xn, we can partition them into clusters, such as shown here. And like the C5 cluster here is a set of points that were drawn from the fifth Gaussian in the mixture. We, of course, don't know this clustering, and that will be the goal of the talk, whether we can recover it. Okay, so let me define what it means to be a 99% accurate clustering. Recall C1 to CK was the true partition of the set of n samples that we have. And a partition A1 to AK is 99% accurate if we can recover 99% of each of the clusters. In other words, the part of the cluster that we don't recover for any cluster is at most 1%. So that's a fairly intuitive notion of accurate clustering. Let me then talk about when this is possible. So I want to focus on this notion of being pairwise well separated in total variation distance. So here, every pair of Gaussians that appear in our mixture are TV separated. In particular, the TV distance between any pair is at least 1 minus delta, where you should think of delta as some constant, possibly a function of k. And I would like to point out that in some sense, this is the weakest possible notion of separation under which you can still cluster, because recall total variation distance intuitively measures overlap among distributions. And if the overlap is small, then you can hope to information theoretically cluster, and if it's not, then there is no hope. Pictorially, it's easy for us to see that clusters such as C3 and C5 are pairwise separated in total variation distance simply because their means are far. But I claim that clusters such as C4 and C3 are also separated in total variation distance. And you can see that by projecting along this direction, these two Gaussians look really different. Another notion of separation, which is captured by TV separation, and this is truly a high-dimensional notion, is clusters of the form C1 and C2. So think of these as spheres in high dimension, and we know that Gaussians concentrate around a thin shell, and if the radius of this shell is different, then the resulting Gaussians are still clusterable, even if their means are the same. So there are some intuitive examples that are captured by TV separation, but there are also some funny examples that are captured. And we would like to cluster all such mixtures. I like two more examples, so I'm going to tell you about them. So in one dimension, consider a mixture of these two Gaussians. Again, it's an equiweighted mixture. The green Gaussian is a standard Gaussian, mean 0, variance 1. And the purple one is, again, mean 0, but variance 10. And this mixture of Gaussians is also clusterable. And one more example is a mixture of subspaces. So consider two Gaussians with the same mean and covariance. but they lie, or roughly the same mean and covariance, but they lie in subspaces which are not exactly the same. You can make the angle between these subspaces really small and ensure that parameter distance between the pairs of Gaussians here is small under any norm that you want to consider. But the total variation distance is still going to be 1 if the subspaces are different. And we want algorithms that can cluster all such mixtures. Okay, so now let me talk about what it means to be outlier robust. The corruption model that we consider is to draw n samples from a distribution D. In our case, this is going to be a mixture of k Gaussians. And then we let an adversary corrupt an epsilon fraction of the points arbitrarily, even looking at the description of our algorithm. So this is known as the strong contamination model, where the adversary is allowed to, both add and delete points, basically do whatever they want to an epsilon fraction of samples. This notion of corruption generalizes other contamination models that you may have heard of, such as the Huber contamination model. Okay, so now I'm ready to describe the problem. We are given as input an epsilon corrupted set of samples, y1 to yn, from our mixture of k Gaussians, which is well separated. And the goal is to output a 1 minus epsilon accurate clustering of these samples. And the cartoon here has been updated to indicate the outliers that were introduced by the adversary. Okay, so that is a problem that we consider. And mixtures of Gaussians have received significant interest over the years. And let me give you an abridged history of what is going on. So the first generation of results in the TCS community, at least, happened in the late 90s and early 2000s, where people were interested in clustering mixtures of Gaussians under strong notions of mean separation. The next generation of results actually went beyond the clustering and gave algorithms to learn parameters even when the mixture was not clusterable to begin with. And these results are based on exploiting algebraic structure of the problem, and I encourage you to look at them. There's some really cool work here. And in the last 5 years or so, people have focused on developing robust algorithms for several special cases of this problem. Starting with this breakthrough work which estimated the mean and covariance of a single Gaussian robustly. And since then, it was generalized to estimate or cluster mean separated mixtures of Gaussians robustly. So a natural question to then ask is, like, can we cluster all possible mixtures that are separated in total variation distance? And can we do this robustly? Okay, without further ado, this is the main theorem that we present, and we show that we can indeed do this. So to be precise, given an epsilon corrupted set of n samples from a well-separated mixture of k Gaussians, we can recover a 1 minus k to the k times epsilon accurate clustering if we are given d to the k samples in time, which is n to the k to the k. It's a lot of k's. Okay, I want to make some remarks about this theorem. And the first one is that, a lot of prior work in the area really relies on the mixture being drawn from a Gaussian distribution. But we show that this is not really necessary in our work. What we do instead is identify analytic conditions on the distribution. And as long as these conditions are true, we can cluster the resulting mixtures. So what this enables us to do is to extend our result to other distributions, such as mixtures of uniform distributions over the sphere and affine transformations of such mixtures. I would be remiss if I didn't say anything about this k to the k hanging around. And there's a reason for it. So there is a statistical query lower bound by Diakoniklas, Kane, and Stewart, which suggests that this exponential dependence on k is necessary in both the running time and the sample complexity. So at least d to the k and n to the k seems necessary if you consider statistical query algorithms. Of course, there's a gap here. We get k to the k. Okay. And the last thing I want to say about the result is that this notion of clustering accurately is indeed quite strong. From this notion, we can estimate the parameters of each component up to really small error. And we can also recover a mixture that is component-wise close to the input mixture in TV distance. which is essentially the best possible guarantee we can hope for. I'd like to say a bit more about this parameter estimation. So we can get the mean of each component in L2 error scaled by the covariance. We can estimate the covariance in loner ordering. And most interestingly, we can estimate the covariance in what is called relative Frobenius distance or Mahalanobis distance. And it's important that all these guarantees are dimension independent. And these results hold for a wide class of distributions, which is not just Gaussian, so uniform over the hypercube and the sphere. And finally, the last guarantee, the recovery in relative Frobenius distance, was only known for Gaussians prior to this work via a specialized algorithm. So this is also a new contribution of our result. Okay, I'll conclude with some open questions and future directions. Some concrete questions are to improve the dependence on K in the running time and error guarantees, and also improve the dependence on min mixing weight. I focused on equi-weighted mixtures in this talk, but you can maybe have an exponential dependence on the minimum mixing weight as well. Okay, and another interesting question is, what about clustering all mixtures of Gaussians, not just or learning all mixtures of Gaussians? So learning the parameters of all mixtures, even in the case where they might not be clusterable. So think of the case where you have a mixture of Gaussians where the TV distance is close to 0 instead of being close to 1. Can we robustly learn such mixtures? And there was some exciting new work addressing the problem of equi-weighted mixtures of two Gaussians this summer by Daniel Kane. And in the last week or so, there's a new work which extends this to arbitrary mixtures of K Gaussians. And almost as is tradition now in this area, there are two results that do this. One by Alan Liu and Ankur Moitra, another one by myself, Ilyas Nicholas, Daniel Kane, Jia, Pravesh Kothari, and Santosh Rampala. The first one is already available online, and hopefully this one will be soon. Both of these are in submission. And finally, more broadly, we should consider fitting your favorite statistical model robustly, and also looking at what robust estimation can say for inference and supervised learning. A couple of directions I personally like is robust estimators for async models, and robustness and supervised and online learning. I'll stop here and take questions.
Thanks, Anish. Questions for Anish, or actually any of the other co-authors? I see a bunch of people in the participant list.
Oh, I mean, I have a question. Hello,
Yeah.
Can anyone hear me? Oh, yo.
Yeah.
Yeah. So, yeah, just I don't know, like, why K to the O of K? Like,
like why that
why is
particular
it
thing?
why is it not D to the K? Like, what's the bottleneck really? Like,
yeah, I mean, it's a good question. It's hard to summarize in one word what the bottleneck is, but I can tell you in detail, in excruciating detail on Slack if you like.
oh, okay, cool. All right. It's not something. All right, cool.
Yeah, it's not something I can reduce to a few words.
All right, cool.
But it has to do with there's like a hard case. Okay, I mean I'll just take it
All
off.
right, cool. Never mind. All right.
Other questions for Anish? If not, I can stick in a short one. So I guess somehow like the technical meat lies in making this like a TV lemma, whatever, like a characterization into like an SOS kind of proof, right? Is that sort of where the difficulty lies? And so can you like say something short and informative for like what's kind of the difficulty and how to circumvent it?
Right. Okay. So one thing that we do is use this TV separation to show that mixtures of Gaussians can be separated in basically 3 ways, and these 3 ways involve some affine invariant parameter distance. So once you have we call them like mean separation, which is fairly intuitive. Another one is like being separated in a spectral sense. And the third one is like being separated in this Frobenius sense, like Mahalanobis distance. And these correspond to the three pictures I showed before. And, like once you have this property, you want to come up with, identifiability proof in the sum of squares framework that shows you that you can cluster once you have at least one of these three notions of separation. Okay, so that's where like most of the work lies.
Thanks. All right. So next paper up is collaborative top distribution identifications with limited interaction. And I think Nikolai is giving the talk. I saw him at some point in the audience list. Yeah, there we go. Perfect. Take it away, Nikolai. You are not audible, by the way. I can see your slides, but I can't hear you.
I see. Okay, now it's good, yeah?
Now it's good, yes.
Okay, good. So, yes, thank you for the introduction. And I will present our joint work with the ChainJunk and Yuan Zhou. So let's start with the high-level motivation behind our problem. So one of the fundamental questions in the machine learning is to how to make algorithms scalable or distributed. And one of the natural way how we can introduce the scalability or distributedness in our algorithm is the following. We can introduce a lot of engines that will work in parallel simultaneously and try to optimize the objective function in collaboration and exchange some information from time to time. So, and as we know from the real life, the collaboration, it can be really very useful, and also it can be very expensive. And when I speak about usefulness in the context of machine learning algorithms, I basically speak that in parallel, we can improve the convergence rate of our algorithms or decrease the probability of the error of our algorithms. And when I say about the expensiveness, I basically mean that in distributed systems, each round of communication has some overhead, and basically that related to the network bandwidth, latency, and synchronization issues. So now let me go to the specific problem and specific model in which we are working in our paper. Oh, sorry, and because of these two items, we are interested in a trade-off between the number of rounds of communication and the quality of our algorithm. So yeah, so basically let me move to the specific problem. And in our paper, we work on the top M identification problem in multi-embedded settings. In these settings, we have a set of n arms. Each arm is associated with some unknown distribution that has support on 0, 1 segment, and we want to find m arms with the highest means. And in these settings, in multi-embedded settings, we can get information about distributions only by pulling arms. And when we pull some arm, we get an ID sample from this distribution. Also, in these settings, we assume that each pull takes a unit time, and we just ignore other kind of computation from the running time of our algorithm. And in this presentation, I will mainly speak about the specific problem when we are trying to minimize the probability of mistakes that we will not output the correct set of m arms under the fixed running time t, or under the fixed budget on the number of pulls to our environment. So, and let me speak about our collaborative learning model for the multi-embeddeds. In this model, we have n arms, and additionally, we have a k agents, and our learning is split into rounds. In each round, each agent makes the same number of pulls. After that, agents communicate, exchange some information, modify their policies, make some number of pulls again in parallel, and independently communicate again, and so on. So basically, at the final round, they communicate and output the answer. For our specific problem, it is a set of m arms with the highest means. So, okay. Let me summarize. We're interesting in the following problem. Under the fixed running time t, we try to minimize the number of rounds of communication and the probability of the error. And clearly, there is a trade-off between these two values. So if we increase r, the number of rounds, then agents have more freedom, they can exchange information more frequently, and basically, they should decrease the probability of the error of our algorithm. And also, I would like to note that according to our model, in total, agents make t times k pulls, because it is a bound on the running time of one agent, and they work in parallel. So, okay. Let me summarize some previous results for this problem to give you some picture. So in the centralized settings, when we don't have any communication and we have only one agent, the best known result is the following, that for fixed running time t, we can achieve the following probability of the error. Here, h is some instance complexity for the top m problem from the Bandit's literature, and basically it is the best possible result up to some small factors in the probability of the error. So if we go to the collaborative model for some k, Tao, Zhang, and Zhou present some work for top 1 problem, for the specific case of our top m problem, and they present the following algorithm, which can do the following, that for any r, this algorithm can achieve the following probability of the error by using big of r rounds. And now I will compare our result for the general m with this specific one for the m when m is equal to 1. So our Gannet is similar. So basically, if m is small, this algorithms almost matches in the guarantees, but if m is large, we basically have some additional term log of log m over log k. And also, I would like to know this both results are almost tight. So basically, we have a lower bound that says that we cannot outperform these algorithms. So I would like to compare our result in a specific case when the parameter r that controls the trade-off between the number of rounds and the probability of the error is equal to 2. In this case, the previous result says that if we want to achieve such probability of the error with the square root k factor in the exponent, we need only the constant number of rounds. But for general m, we need a log of log m over log k rounds if we want to achieve the same probability of the error. So basically, in our work, we prove the lower bound that says that it is optimal, that we cannot remove this log of log m over log k term. So thus, we show the strong complexity separation between these two problems, when m is equal to 1 and the general case of m, which is pretty surprising because in other models, we don't see such a big gap between these two problems, and the complexities of these problems looks sometimes similar. Yeah, but it's very surprising that we have such big gap for this model. So let me summarize our main result in our paper. For basically, we proved that for any r, the parameter that controls the trade-off, we can achieve the following probability of the error by using such number of rounds r plus log of log m over log k. And we prove the lower bound that this algorithm is optimal, and we cannot outperform this algorithm. And I would like to note that in my long version of the presentation, I highlight some items from the upper bound, but both of these results are highly untrivial and requires nice ideas and nice construction of hard instance and some nice ideas for the upper bound and lower bound too. So basically, let me summarize our main messages and contribution of our paper. So as I said, for the fixed time version, when we fix the running time and try to minimize the probability of the error, we achieve almost tight upper and lower bounds. And we prove the strong complexity separation between top 1 problem and top m problem. And also in our work, we consider the fixed confidence regime when we fix the error of the probability and we are trying to minimize the running time of our algorithm. And in these settings, we also prove some tight results, some upper and lower bounds. And also we show the strong the separation between complexities in the fixed confidence and the fixed budget regime. And I would like to note that the collaborative model is relatively new. It appeared, I mean, it was systematically started to study only 1 year ago. So basically, we don't understand the speed up which the collaborative learning model brings to reinforcement learning, to other problems, and we don't understand the situation. Even such small generalization, not small, but I mean just even such generalization, natural generalization from top 1 to top m requires a lot of new ideas and new techniques, and I think it's pretty nice. So yes, basically, thank you for the listening.
Thanks, Nikolai.
Yeah.
Questions for Nikolai?
So, do you have more comments on the gap between the fixed confidence and fixed time horizon? Because I don't think you showed us the exact gap is, right? And you can talk a little bit more about that. I'm interested in learning.
What do you mean?
No, I mean like just the last slide. You said there's a gap between the fixed confidence.
I see. Basically, the situation is the following. The round complexity of the problem in the fixed confidence regime depends only on the instance, and it doesn't depend on the number of agents. But in the fixed budget regime, actually the complexity depends on the number of agents and the parameter m. I mean,
I see.
Yeah. Yeah.
I see. Okay.
Other questions? If not, I can throw in a short one. So could you maybe say a few words how the lower bound instance looks?
Okay, so
if you can, if it's too complicated.
Yeah, it's not simple, but it looks like it's based on some problems that you cannot identify with a good probability. You cannot identify the number of ones in 0, 1 vector, in the vector from 0 and 1, and basically after that we embed this problem into in the top m problem, and actually after that we need some hierarchical construction, how to some kind of round elimination arguments. Just we need to embed some hierarchical construction and make some induction during by rounds. I mean, just it's so yes.
Cool.
Okay.
Thanks.
Yeah.
More questions? Okay, if not, we can have the next speaker set up. I suspect we'll have Navid. So we have kernel density estimation through density constraint nearest neighbor search. This is a paper by Moses, Michael Kapralov, Navid, and Paris Simonalakis. And I suspect Navid is giving the talk. Yeah.
Yeah.
I can see the screen.
Can you hear me?
Yes.
Okay. Can you see my screen?
Yes.
Okay. Should I start or?
Maybe give it a minute. I mean, I think probably I've been tracking the participant list. Everybody has been here more or less from the beginning, but just so that we keep time, maybe let's give it one more minute. But
sure.
Yeah. You're visible, audible, and screen is also visible.
Sure.
Okay, you're good to go.
Okay. Hello, everyone. My name is Navid. I'm going to talk about our recent result in kernel density estimation. This is a joint work with Moses Charikar, Michael Kapralov, and Paris Siminelakis. Since the talk is about kernel density estimation, I need to start with kernel functions. Kernel functions receive 2 points as input, and their output is a quantity that measures similarity between these 2 points. For the purpose of this talk, the main property that we care about kernel function is that they are decreasing functions of the distance between these 2 points. For instance, you can think of Gaussian kernel, exponential kernel, and etc. Suppose that we have a data set P in our space RD, that this set P has size n. Then kernel density at some point Q is defined as the average of kernel values between points in this data set and this point Q. We usually denote this value by mu. These points in the data set can be viewed as samples from some density function, and this kernel function is going to smooth out these samples so that this generalizes to the whole space. In kernel density estimation problem, again, we have a kernel function k, a set of points p of size n. In the pre-processing phase, first we are going to prepare a data structure. Then in the query phase, we are given a point q. Our task is to output a 1 plus minus epsilon approximation to kernel density at q. For simplicity, let's assume that epsilon is constant, and we want to succeed with constant probability, and d is polylog n. This last assumption is actually without loss of generality. This problem has many applications in machine learning, statistics, and data analysis. Let's start with a trivial solution. A trivial solution just tries to calculate kernel density exactly. So it goes over all the points. So it means that this data structure needs space and query time linear in the number of points. Since we are estimating summation of some quantities, we can also do random sampling. In random sampling, in the pre-processing phase, we sample a data point P uniformly from our dataset. And in the query procedure, we just output the kernel value between this point and our query. Is it a good estimator? We need to check 2 properties. First, we need to check if it is unbiased. And second, we need to check its variance. We want to do the analysis for random sampling more carefully, because this is going to give us a benchmark for efficiency of our data structures. For the first moment, we can easily see that expectation of this estimator is mu, so it is unbiased. For the second moment, we can upper bound expectation of z squared by mu, just noting that kernel values are upper bounded by 1. This suggests that we need order 1 over mu samples to get a 1 plus minus epsilon approximation to our kernel density. So the space and query time of this data structure is order 1 over mu. This suggests that we can state space and query time of these data structures in terms of mu. And you can think of mu as some quantity between 1 over n and 1. Charikar Siminelakis, in their FOCS 17 paper, were able to beat random sampling and achieve space order n over root mu and query time of 1 over root mu. In the follow-up work of Bachkurs, Charikar, Indik, and Siminelakis in FOCS 18, they were able to achieve linear space and constant query time for smooth kernels, such as polynomially decreasing kernels. And more recently, Bachkurs, Indik, and Wagner, in their NeurIPS paper, were able to improve the space of FOCS 17 paper and achieve space order 1 over mu. In this work, in the first part, I'm going to talk about a data-independent approach that is easy and clean. It is so easy that I'm going to give you almost all the details even in this talk, and it already improves upon or matches all prior work in this area. For instance, for the Gaussian kernel, we are going to have a data structure that has a space order 1 over mu and query time 1 over mu raised to 0.25. In the second part, we did a more technically involved data-dependent approach that improves upon the first part of the result for a broad class of kernels, but not all of them. For instance, for the Gaussian kernel, we can improve the query time to 1 over mu raised to power 0.173. So in random sampling, we were choosing points uniformly random from our set. But what is the right distribution to sample points from? This leads us to importance sampling. In importance sampling, we want to ideally sample points with probabilities proportional to their contribution. More specifically, in this problem, we want to sample points with probabilities 1 over n mu times their contribution. 1 over n mu is the right normalization factor since these kernel values sum to n mu. So in importance sampling, basically we are sampling points with higher contribution with higher probability. In this problem, which points have higher contribution? The answer is the points that are closer to our query. This leads us to locality-sensitive hashing schemes. These are space partitioning schemes that hash points into some buckets that closer points have higher chance of colliding with each other compared to far points. This has many applications in approximate near neighbor search problem, range reporting, and etc. And it has received a lot of attention in the recent years. The hash family that we are going to use in the first part of this paper is called Andoni-Indica LSH that uses ball carving to partition the space. And the guarantee is that if 2 points P and Q are at distance R, the collision probability is some Gaussian in R. Charikar-Simonelakis, in their FOCS 17 paper, used this LSH as a sampling tool. It enabled them to do a version of importance sampling, but the problem is that when you do this LSH sampling, then there are some dependencies caused by the geometric structure of the problem. On the other hand, in our approach, for different distance levels, we are going to first sample the dataset, then we are going to use LSH for recovery. This enables us to implement ideal importance sampling. Actually, the thing that allows us to do this efficiently is the density constraints induced by kernel density. Before going into more details, I need to start with some simplifying assumptions. First, assume that we have a constant factor approximation to mu, and simply call it mu for the purpose of this talk. The second assumption is that we can scale points in such a way that the kernel values are just mu raised to power distance squared by 2. And the third assumption is that we have no points beyond root 2 from the query. These three assumptions are without loss of generality. So in our approach, if a point is at distance x, we want to sample it with probability 1 over n times 1 over mu raised to power 1 minus x squared by 2. So let's do the following. For any distance x, first sample the dataset with this rate, and then prepare a data structure such that when a query comes, if a point is at distance x, we should be able to recover it efficiently with high probability. We are going to use Andoni-Indica LSH for recovery. This means that in the pre-processing time, we are going to use Andoni-Indica LSH for hashing points. And in the query phase, we are going to scan queries bucket for points at distance x. The efficiency of this algorithm comes from the size of the hash bucket that corresponds to the query. So we want this to be constant. Let's do the query bucket size analysis. We are going to do a simplified version here. Let's just count the number of points that we are going to get from distance root 2 in queries bucket. Initially, we can have at most n of them since the data set is bounded by n. Then we are going to subsample this data set. So we are going to have 1 over mu raised to power 1 minus x squared by 2 of these points in expectation. And assume that the collision probability under Andoni-Indica LSH is mu raised to power 2 alpha. We are going to set alpha. And this is by just concatenating a couple of these hash functions. So this means that after subsampling and LSH, I'm going to have 1 over mu raised to power 1 minus x squared by 2 minus 2 alpha. So remember that I wanted constant size query bucket, so I need to set the exponent to be 0. This means that alpha is 1/2 times 1 minus x squared by 2. Here I just did the analysis for distance root 2, but I'm just flashing some slides that does this for other distances as well, And it's just simple arithmetics. And we can see that the worst case happens when y is equal to √2, and that's the right exponent to set alpha to. Now we can do the query time analysis. For the query time analysis, remember that we want to recover points at distance x from query. So we are going to collide with them with probability mu raised to power x squared by 2 times 1 minus x squared by 2. So if we want to recover them with high probability, we need to repeat the whole procedure 1 over this probability time. This means that for any distance x, my query time is bounded by 1 over mu raised to power 0.25. And we just repeat this for order log n distance levels. The space analysis is the same, and we just need to mention that we sample points with some rate, and we hash them a couple of times. And this shows that the space is bounded by 1 over mu. So in general, the result statement for Gaussian kernel is as follows. Space is order 1 over mu, and query time is 1 over mu raised to 0.25. The approach is general, and it can be applied for other kernels as well. Now, what if we use data-dependent LSH instead of Andoni-Indic LSH? This has received a lot of attention in the recent years. If we replace the Andoni-Indic LSH by data-dependent LSH, the main challenge is the query time analysis of this data structure. Since data-dependent LSHs are quite complicated, and it's not easy to analyze the density evolution over the time, we took a bunch of technical steps to reduce the query time analysis of this case to a linear programming that we solve numerically. And the result statement for Gaussian kernel is that space is order 1 over mu, and query time is 1 over mu raised to power 0.173. This approach is also general, and it can be applied on a broad class of kernels, but not all of them. Here I can state some open questions in this area. One, we need to find a data-dependent analysis that is actually simple. This raises the question, can we have a simple data-dependent approach for ANN problems? We actually took some steps in this regard, and we made some progress in this work, but I think there is much to be done there. The second question is that what is the optimal exponent for this question? We still don't know what is the optimal exponent for this. And the final question is, can we get a practical version of the second part of this paper? Thank you, and I would be happy to answer questions.
Thanks, Navid. Questions for Navid? I can kick things off until people think of a question. So I guess one of your questions is an optimal exponent. I guess probably given the kind of the weird exponent that you're getting with the data-dependent analysis, like I suspect you don't think this is like the kind of like the right exponent. It's just like a kind of artifact of the analysis. And like, do you have a conjecture what what these methods should give?
Actually, the exponent that we get is like, it's not that weird. It's actually 3 minus 2 root 2. Actually, we couldn't do it exactly because we solved the linear programming numerically. But this is close to 3 minus 2 root 2. Actually, I don't know. It depends. If we are going to use LSH schemes for this problem, probably we can get some lower bounds that shows that our result is actually optimal. But also we were wasteful in some regimes, so probably there is space for improvement.
Cool. Ainesh asks, does the 0.173 exponent require Gaussians, or is it sufficient to just have sub-Gaussians?
If the kernel function is decreasing slower than Gaussian kernel, it means that we are going to get better exponents. That's actually generally true. If the kernel is reducing slowly, it means that the problem is easier, because it can be reduced to some easier case of approximate near neighbor search problem.
Great. Thanks, Navid. And I guess we are approaching the last talk of the session. So the last one is small covers for near zero sets of polynomials and learning latent variable models. It's by Elias and Daniel Kane, and I think Daniel is giving the talk since I saw him in the audience.
Okay, should I get going?
You can indeed get going, yes. You're audible.
Okay, yeah. Hello, yeah, I'm talking about small covers for near zero sets of polynomials and learning latent variable models. This is joint work with Elias, Diacon, and Colas. To get us started, let's talk about Gaussian mixture models. So here we're going to let X be a mixture of K spherical Gaussians in Rm. So it's, you have these K different mean vectors in Rm, and you pick a random one of them with some probability distribution, and then you return a random point from the identity covariance Gaussian centered at that point. And the goal is we'd like to learn this distribution. So given sample access to this mixture X, you would like to learn some distribution X hat so that the total variation distance between X and X hat is less than epsilon. And so a couple comments about the models. Gaussian mixture models in general are one of the oldest and best studied latent variable models in the literature. And it might be slightly more natural to consider mixtures of Gaussians with arbitrary covariance rather than these identity covariance ones that we have. However, there are known m to the k lower bounds, at least in the statistical query model, for learning mixtures of arbitrary Gaussians. So restricting our attention to the spherical case gives us some hope that we might be able to get bounds that are sub-exponential in the number of components. So looking at this problem for the spherical Gaussian case, what's known? Well, information theoretically, it's known that about mk over epsilon squared samples are necessary and sufficient to learn the distribution. However, algorithmically, things seem like they might be a lot harder. The best known algorithms previous to this work have runtime that are exponential in k. And so there's a pretty big gap here between the upper bounds and the lower bounds. And so the question that we're going to ask is, what can we do to close this gap? And we're going to try and work on the algorithmic side. And the basic technique is a pretty common one. We're going to look at the method of moments. We'd like to compute low degree moments of the distribution X, and then use those moments to learn the distribution. Now, before we talk about this in too much detail, it'd be good to know what the low degree moments of this mixture of Gaussians are. And it's not too hard to see that learning all of the low degree moments of this particular mixture X is equivalent to learning the low degree parameter moments of the mixture. And so this is, for various values of D, the sum I is 1 to k of wi times mu I tensor to the D. And learning this tensor is basically equivalent to learning the higher moments of the distribution that you would get if you just took the associated probability distribution over the centers of these Gaussians. And we're just saying, so you learn the sort of moments of the parameters, and that is, it turns out, equivalent to learning the moments of the actual distribution. Okay, so this is what we can learn with our moments. And unfortunately, there is an obstacle. And in particular, the moments alone are not enough to identify the distribution, at least until you learn an awful lot of them. So even in one dimension, you can construct a pair of mixtures of k Gaussians, say x and x prime. I'm thinking of these as sort of the red mixture and the blue mixture here. So that the first k minus 1 moments of x agree with the corresponding moments of x prime. But the total variation distance between these two mixtures is far. And so if all you have learned is k minus 1 moments of the distribution, you can't tell whether you have the red mixture or the blue mixture, and you can't learn the distribution to small total variation distance. Now, in one dimension, you can get around this problem because there are exhaustive techniques to learn a mixture in one dimension. You can sort of take your line and chop it into tiny intervals and learn the probability in each interval, and that's sort of good enough to approximate by a piecewise constant function or something. However, you can sort of thwart this algorithm by just embedding this example into high dimensions. So you pick any line that you like in m dimensions, and you place the centers of your Gaussians in exactly the same pattern along that line. And it's still the case that you'll have this moment matching pair of distributions, but now they're in m dimensions instead of 1. And in m dimensions, if you want to distinguish these just by looking at their moments, you need to compute the first k moments, which is going to take something like m to the k time to even just write down what those moments are. Okay, but it turns out that this particular example is also easy. If you look at the second parameter moment matrix, this is basically the matrix sum of wi mu I transpose, you'll note that the image of this matrix M, which we can compute, is just the span of the means mu I. And so in this case, where the spans all lie on a line, or the means all lie on a line, the span is a 1 or maybe 2-dimensional object. You can compute M, project everything onto this 1 or 2-dimensional space, and then, as I said before, there are exhaustive techniques that you can perform to solve this problem quickly. It should also be noted that in general, this kind of technique is sort of well known for this problem. In general, you can use this to reduce the problem to a k-dimensional problem. Okay, so let's find a harder example that thwarts this as well. This other technique only worked because all of our samples literally lie on a low-dimensional subspace. So I'm going to start with this low-dimensional moment matching construction. And then I'm just going to add some extra components to each distribution. So these purple components are part of both the red and the blue mixture, and they're basically added to make sure that things don't all lie on a low-dimensional subspace. So you can construct 2k mixtures of Gaussians, x and x primes, so that they match k moments, and they span k-dimensional subspaces. So you can only dimension reduce to k dimensions, and then you need to compute something like k moments, and it doesn't really work. Okay, so we know that you cannot identify x and x prime exactly with just a few moments, but what can we hope to do? Well, the thing that might be possible is we can identify these sort of noisy components that we added, and then we can't identify exactly like what the centers were in this moment matching distribution, but hopefully we can identify the line on which this moment matching distribution takes place. And so that's sort of our goal. The question is, how the heck do we do this? And the basic idea is the following. If we know the parameter moments up to degree 2d, then that means that for any polynomial q of degree at most 2d, we can compute the sum of wi q of mu I. Now what we're going to do is we're going to let q be the square of some lower degree polynomial p. And so then we get this quadratic form. Q of p is at least approximately the sum of wi p squared of mu I. And we note that q of p is 0 if and only if p of mu I is 0 for all I. And what can we do with that? Well, if we compute this subspace of polynomials that nearly vanish with this quadratic form, which we can do because it's positive semi-definite, this gives us a big subspace of the space of degree d polynomials. In particular, it's going to be codimension at most k, due to the fact that we have only sort of these k linear constraints. And we know that these polynomials nearly vanish on every single one of our means. So what do we do with this? Well, here we have this giant technical lemma, which says, suppose that we have a subspace of codimension at most k within the set of degree d polynomials. We've got a few parameters that I'm not going to talk about in too much detail. I'm going to let S be the set of points in Rm, such that x is contained in a ball of radius r, and such that for every polynomial in this set V, the absolute value of p of x is maybe not 0, but is very tiny. It's like delta times the size of p. Then there exists a cover of S by epsilon balls. The number of balls in this cover is, something reasonable to the d squared times k to the 1 in d. And furthermore, such a cover can be computed in time polynomial in M. So a couple notes, the basic form of the cover size is approximately optimal. We have like an extra d in the exponent and some extra terms in the base, but you can show that you need something like that. This delta that we have does actually seem to need to be pretty small in order to guarantee that this set isn't too thick. And the proof is basically elementary. It uses linear algebra and principal component analysis and things like that, but it is quite involved, and I do not have time to go into it today. But once we have this result, what can we say? We computed a cover, and we know that every mean in our mixture with non-trivial weight is close to some element of this cover. Now, if we take all of our means and round them to the nearest element of the cover, that's only going to change our distribution by something like epsilon in total variation distance. This means that we have an explicit set of distributions and know that the x that we're trying to find is epsilon close to some mixture of these distributions. Now, that general problem can actually be solved. You can compute a maximum likelihood estimator for writing x as such a mixture. And it's not hard to show that in polynomial time in the size of your set of hypotheses, you can solve the problem. And so the final result is that we have an algorithm for learning a mixture of k-spherical Gaussians to error epsilon. It takes time and samples poly m over epsilon to reduce to k dimensions, and then k over epsilon to the O of d squared times k to the 1 over d to deal with it after that. And if you set d to be log k, this is quasi-polynomial in k over epsilon. And remember that previously the best known algorithms for this problem ran in time exponential in k. So we haven't quite closed the gap to the lower bounds, but we've made tremendous progress here. Finally, I'd like to say that spherical Gaussians are not the only application of this. This is a pretty general technique for learning latent variable models. The idea is you want to learn the parameter moments, and hopefully you can do this. Then you use our structural result to compare, to compute a small cover for the set of parameters. And then you run some kind of algorithm that's exhaustive in the cover size. And so in addition to having this quasi-polynomial time algorithm for learning mixtures of spherical Gaussians, we have new results for learning positive linear combinations of ReLUs, learning mixtures of linear regressions, and learning mixtures of hyperplanes. All of these results are the first that are quasi-polynomial in the number of parts in the mixture, whereas the previous best known algorithms ran in time sort of exponential in at least k to the some constant. Okay, that's all I had to say. Are there any questions?
Thanks, Daniel. Very cool. Questions for Daniel? If not, I can kick one off until we're waiting. So for these, like, I guess, target applications you've listed, for which one is like the kind of, I guess, the improvement in runtime from the previous best sort of the largest, I guess, like, you know, is there like a kind of like some particular target application where there's like a really large improvement in runtime?
I mean, all of these are pretty large improvements. All of these, the algorithms that we provide are quasi-polynomial in relevant parameters. Whereas for basically all of these, the previous best known algorithms had runtime exponential in some power of k.
Cool. Inesh asks, is there any hope to extend these techniques to adversarial outliers?
Is there any hope to extend these techniques to adversarial outliers? I mean, there's some hope. There are major difficulties with doing that. In particular, like for this cover result to hold the way we've stated it, I mean, we really need this delta, which is sort of we know that these polynomials vanish to some error delta, to be very, very small. It needs to be, epsilon over some parameters raised to the dth power. And we just can't learn the moments to enough accuracy to do that with respect to adversarial outliers. And so, and in fact, the cover that we're hoping to compute is just not possible with adversarial outliers. And so in order to make this sort of thing work in that context, we're going to need to come up with some sort of relaxed notion for what kind of cover we can compute. And it would be nice to get this stuff to work. It will require major improvements on the technology.
Cool. I think that's it. Any last call for questions? All right. Thanks, Daniel. And that was it for this session. See you guys later.